Welcome to the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our second lecture covering material from Chapter 10. The historical gas laws are the relationships that we learned in our previous lecture, specifically Boyle's, Charles, and Avogadro's laws. These work as long as only one property of the gas is changing. It is actually more common to have more than one property change. The historical gas laws can be combined to form the combined gas law, which can be used if more than one property is changing. Under typical conditions, the amount of gas is held constant, so we can eliminate the N. The combined gas law is most often used to calculate a new pressure, volume, or temperature of a gas sample when two of these properties have changed. The ideal gas law incorporates the three historical gas laws in a constant, which is given the symbol R and called the universal gas constant, or the ideal gas constant. Notice the units of R. Because of these units, it's very important that our volume is in liters, pressure in atmospheres, and temperature in Kelvin. When three of the four properties of a gas sample are known, the ideal gas law can be used to calculate the unknown property. We can derive an equation from the ideal gas law to solve for the molar mass of a gas. The idea is that the formula for molar mass can be rearranged so that the number of moles is equal to the grams over the molar mass. We can then substitute this for N in the ideal gas law. We can do the same thing for density. Since density is mass over volume, we can replace both of these in the ideal gas law with a symbol for density. Again, it's really important to keep track of your units. Since we're using the constant R, our pressure has to be in atmospheres and our density is going to have units of grams per liter. This is just a sample problem where we determine the molar mass of a gas. You should be able to do this on your own. The formula would be provided for you. STP refers to standard temperature and pressure. These are a set of conditions of temperature and pressure that are often used when conducting experiments. The standard temperature is 273.15 Kelvin, that's 0 degrees Celsius, and the standard pressure is 1 atmosphere. If we use these conditions in the ideal gas law and solve for volume, we will get 22.4 liters. And what this means is that 1 mole of any gas at STP will have a volume of 22.4 liters. Since we can calculate the number of moles of a gas using the ideal gas law, we can apply stoichiometry problems to gases. Using the mole island roadmap, you can see that we can get the moles of a gas if pressure, volume, and temperature are known. Gases have pressure. When the gases are combined, their pressures are additive. You can see in this slide that half the number of moles will result in half the pressure even if the gases are different. When combined, the resulting pressure is the sum of the individual pressures. There is a relationship between pressure and number of moles of gas that's directly related. We can use the mole percent of a gas in a mixture to find the pressure contribution by that gas if the total pressure is known. Mole fraction is represented by the letter X, often with a subscript indicating the gas. The mole fraction is similar to percent composition in that it's the number of moles of gas over the total number of moles. These are often given as percents. In this case, we can divide the percent value by 100 to get the mole fraction. There are no units for mole fraction, and the sum of the mole fractions for all the gases present will be 1. This is another example problem. You should be able to complete it on your own after you study this a little bit. Notice how we had to get the balance percent N2, and we just took the two provided percents and subtracted them from 100. Here's a detailed answer to that previous question. And lastly, we'll end the lecture with an additional practice problem. The amount of argon present is 10.5 moles. Try this problem later without the work shown and see if you can solve it on your own. If not, keep trying. A little practice will go a long way when studying chemistry. Thanks for watching. Please give the video a thumbs up and subscribe if you would like to see more of these mini lectures on the Professor's DuBois channel.